When we look again, as I said previously, mass number, it's the number of protons and neutrons because they weigh 1 atomic mass unit. They're not always the same. So let's take hydrogen, for example. So hydrogen can have, it exists as 1 proton, 1 electron, and no neutron. And that's going to give it a certain mass number of 1, okay? But then if you go to deuterium, deuterium is a type of hydrogen, but it's a different form, and it's a different form because there's a neutron that has popped into that nucleus with the proton. And so this is going to give this atom a mass number of 2. So it's a form of hydrogen, but it's different because it has a non-charged molecule in there, a neutron. Tritium is similar, except it has 2 neutrons added. And again, no charge, but there is weight. So the weight's going to go up to 3, but the charge of tritium is not going to change from hydrogen. Isotopes are going to be structural variations of elements that differ in the number of neutrons they contain. So these 2 things that I just showed you right here, deuterium and tritium, these are isotopes. They're forms of hydrogen, so they're hydrogen isotopes. The atomic weight that we see here again in the box is going to be the average of mass numbers of all the possible isotopes this atom can have. So the average weight here for hydrogen will be 1 plus 2 plus 3 divided by 3, if that were all the isotopes for hydrogen. So this is important because when we can use these isotopes and their characteristics for having these extra neutrons. We can use those elements in our favor to do things. One example is going to be imaging. But basically, these isotopes are just not as stable because they have these extra neutrons in them. And so they will spontaneously decay to get to the more stable form. And when they do that, they give off radiation. So when they're getting rid of a neutron, let's say this is a neutron, to get into that more stable element form, they give off energy. Well, we can harness that energy. We can detect it with scanners. And so this is a super helpful tool for research and in medicine. So you may have heard or seen of labeling with radioisotopes. That is what we're doing. So we're able to harness the energy that's given off when those elements are trying to get to a more stable form. And it can be diagnostic, which is where we see it a lot of times, but it can also even be therapeutic. Some cancer treatments involve radioisotopes. This giving off or releasing of energy when a neutron is released is damaging to living tissues. So this can have, as you might imagine, a positive effect or a negative effect. So in our therapeutic example, like I said, it's useful against cancers. So if we use these radioisotopes in a tissue region that has been infected with cancer or constantly dividing cells, this energy can actually kill those cells and help remove the cancer. However, we also have radioisotopes that exist sometimes in bad water, bad and toxic environments, and this can actually cause tissue damage to perfectly healthy tissue. So an example of that would be radon from uranium that is sometimes leached into the ground and gets into the groundwater, and that can start to ruin lung tissue and cause lung cancers. So radioisotopes can be harmful, but they can also be useful.